this webinar is about answering complex hierarchy questions in network meta-analysis. And what I mean by complex is questions that cannot be answered with the ranking metrics that are regularly used in network meta-analysis. But before starting, I would like to start with a question. So, Dario, you could bring up the first question, which is how many network meta-analysis have you conducted so far? None, and I currently don't plan to do it. None, but I plan to do it. 1, 2, 3 or more. And let's wait for the results. So I see that, yes, many people are quite experienced with network meta-analysis. So a fourth of the attendees has already conducted 3 or more network meta-analysis, and but there are also some people that have not done a network meta-analysis. So almost 50%, so half of the participants have not done a network meta-analysis, but most of them are planning to do it. So I will just use this slide as a reminder for the basic principle of network meta-analysis, which is to use both direct and indirect evidence in a network of interventions. And the major advantage over pairwise meta-analysis is that it can give valuable insights for the benefits and harms of multiple alternative treatment options. So let me just one moment. Stop sharing. If, say, we have a triangle, an operative triangle of 3 treatments, A, B, and C, and we have studies that are comparing A and B and A and C, the basic idea of network meta-analysis is to derive an indirect effect for B versus C via the common treatment node A. And in case that we have also direct evidence for B versus C, then we can synthesize the direct and the indirect effect into a network meta-analysis treatment effect. And what is usually the case is that we do not only have 3 treatments, but we have a larger network of treatments that are available for a healthcare condition. And then the network meta-analysis B versus C treatment effect will get information not only via the A treatment node, but via all nodes in the network. And the major output of network meta-analysis is a set of all relative treatment effects. And what I mean by all is that all treatments versus each other. So A versus all other treatments and B versus all the rest and so on. And a second output of network meta-analysis is a treatment hierarchy from the most desirable to the least desirable treatment option. So let's start with the relative treatment effects as a result, the major result of network meta-analysis. So for relative treatment effects, there are several ways that can be presented. And one of them is to present them in a forest plot, but usually we only present a subset of them in a forest plot. And the subset that we are presenting is the relative treatment effects versus a specific reference, which is arbitrary for the calculations of the network meta-analysis model, but not for the presentation. So here, let's take this hypothetical network meta-analysis A with 18 treatments, and these are the relative treatment effects measured as odds ratios with their 95% confidence interval versus treatment A14. And as I said, we have the odds ratios and the confidence intervals around these odds ratios versus treatment 14. And now let us consider this second network meta-analysis, again with 18 treatments. And these are the relative treatment effects versus treatment B1, together with the 95% confidence interval. And I want to use these two hypothetical network meta-analysis in order to ask you the following question. So here I will show you the question here, and then we will move to the poll, so you can think about it while looking also at the two forest plots. So the question is, in which of the two network meta-analysis it is easier to judge individual differences between the drugs? In the network meta-analysis A, network meta-analysis B, or it is the same. And what I mean by individual differences between the drugs is in which network meta-analysis you think that differences between the drugs are more clear. So in other words, where it is more clear that treatments are more similar or less similar to each other. There are major or small differences between each other, or the treatments are more or less the same. So is in one of the two network meta-analysis easier to judge such differences between the drugs or not? So I think we can now move to the poll with a question and take your answers. Okay, so the poll is now closed, and what you responded. So many of you responded that in the first network meta-analysis, in network meta-analysis A, it is easier to judge individual differences between the drugs. Very few, 15%, said that in network meta-analysis B, this is the case, and 40% said that this is the same. So this is interesting because this is what, yes, let me, yes. This is what I would probably also answer, that in network meta-analysis A, the individual differences are clearer, but in fact, the correct answer is that it is the same, because the two network meta-analysis that I showed is the same network meta-analysis, and in fact, it's not a hypothetical one, but it is this one of antidepressant drugs for major depressive disorder, and the difference between the two forest plots is just the reference treatment. So here are the drug names next to the odds ratios and their confidence intervals. And on the first forest plot, we have all odds ratios versus fluoxetine, whereas in the second forest plot, we have all treatments versus vortioxetine. And what I want to show with this example is that the forest plot is appropriate for seeing the relative treatment effects versus a reference, but is not appropriate for judging individual differences between the drugs, because the reference treatment that we will use is arbitrary in regards with the derivation of all relative treatment effects, but is not arbitrary for looking at the results, because it might influence our perception on whether the treatments are similar or not, as it did in 46% in this poll. So it might show that on the forest plot on the left, we have more clear distinction between the drugs, whereas in the second forest plot on the right, we have confidence intervals that are more wide, and so the treatments are more similar to each other. So this is the reason that looking at all treatment effects is recommended. And what is usually done in order to do so is to use a league table like this, where in the diagonal we have the names of the treatments, and then at each cell we have the relative treatment effect between the treatment in the row and the treatment in the column. And something that can be done is to use the upper triangle and the lower triangle in order to show two outcomes, or use them to show the pairwise meta-analysis results and the network meta-analysis results. But still, even having this table, which provides all the information that comes from network meta-analysis, again, judging individual differences between the drugs is not easy with such a table. And this is the gap that ranking is coming to cover, to produce a hierarchy, as said, from the most desirable to the least desirable treatment option, where we will attach a value to each treatment. So to see if this holds or not, let's get to our third question. And I would like you to answer, if you have conducted at least one network meta-analysis, whether you have presented some form of treatment hierarchy, yes or no. So the poll is now ended, and 68% of those that answered, so from those that have conducted at least one network meta-analysis, have presented some form of treatment hierarchy. And this is interesting because it is a much larger figure than the one that we had found in 2016 in an empirical study of network meta-analysis that we had conducted, where we had found that 43% of published network meta-analysis did present some form of treatment hierarchy. So again, the usefulness of ranking comes from this, to highlight more clearly the individual differences between treatments, which is possible but less easy with the entire set of relative treatment effects. And what ranking metrics do is to summarize this table in different ways. And despite the usefulness and the common use of ranking metrics, methodologists debate several issues underpinning the ranking metrics from network meta-analysis. The main criticisms are that they are clinically not relevant and that they are difficult to interpret. And thus, looking at all treatment effects is recommended. But what is the answer that ranking metrics answer? This question was something that we wanted to investigate in this paper, introducing the treatment hierarchy question in network meta-analysis, led by Georgia Salanti, where we introduced the notion of treatment hierarchy question, meaning what does each of the ranking metrics answer? And then if we have this question for each of the ranking metrics, we can judge whether the question is clinically not relevant and whether it is difficult to interpret. So I will go through two of the most common ranking metrics, the probability of being the best, or according to the paper I showed in the previous slide, the probability of having the best mean outcome value, and the SUCRA. So to remind how probability of being best and SUCRAs are calculated, let us take this simple network of 4 treatments, where what we do is to compute the probability for each treatment being at its possible position. So here we have A, B, C, and D, and we have the 4 positions, first, second, third, and fourth. And in either in a Bayesian framework by counting the MCMC cycles, or in a frequentist framework using a resampling method, we calculate the probability for each treatment being at its possible rank. And what probability of being best is the first row of this table. So what we answer with these ranking metrics is what is the probability that A is first. For example, here is 25%. And the treatment hierarchy question for this ranking metric is which treatment is most likely to have the best, or in other words, the most desirable mean value on the studied outcome. And having introduced probability of being the best, I would like to go to the fourth question for today and ask you if you think that this ranking metric is clinically not relevant, difficult to interpret, both of the above, or none of the above. Okay, so the poll is now closed, and 8% said that it is clinically not relevant, 39% said that it is difficult to interpret, 34% said that both, and 18% said none. So yes, so I would say that it is not, yes, a very likable ranking metric according to this poll. But in my opinion, I wouldn't say that it is difficult to interpret, but it's kind of answers a very narrow question. So it might be that it is or it is not clinically relevant, but it could be just taking into account that only this row is considered for this ranking metric. And just as a note, having a table like this, we can answer other questions, like, for example, what is the probability that C is second? Here is 50%. And then moving to the cumulative table of probabilities, we can summarize the previous table and have the cumulative probabilities for each of the treatments. So what is the probability for treatment A being first or second, first, second, and third, and so on. So having a table like this, we can, for example, see that the probability that A is first or second is 50%. The probability that D is among the best 3 options is 25%, and so on. And then how SUCRA are calculated, one way to see it is that we take this table and we map it on these graphs, and then the area under the curves for the 4 treatments are as shown here: 0.5 for A, 0.75 for B, and so on. And then the treatment hierarchy question that SUCRA answers is which treatment has the largest fraction of competitors that it beats. Or in other words, the SUCRA for treatment I is an estimate of the proportion of treatments that treatment I is better than. And this leads us to the 5th question, which is whether you think that SUCRA, this ranking metric, is clinically not relevant, difficult to interpret, both of the above, or none of the above. Okay, so very few people said that it is clinically not relevant. Only a third said that it is difficult to interpret, and 15% said that it is both clinically not relevant and difficult to interpret. And there are 45% of the participants that think that SUCRA is both clinically relevant and it is not difficult to interpret. So I would say that participants are kind of divided, like 50-50, whether SUCRA is a good ranking metric or not. And again, there is no right or wrong answer here. It's a matter of opinion of whether you think that this question is a question that deserves to be answered or not. But now going a step further, it could be that there are other questions that are of interest and are of a hierarchy nature, let's say, but are not answered by the ranking metrics that are available. So from the main ranking metrics that I showed, probability of being the best and SUCRAs. So let's go back to the example of antidepressants, of 21 antidepressants for major depressive disorder, where this is the network plot, and the primary outcome is efficacy defined as at least 50% reduction in symptom scales between baseline and 8 weeks of follow-up. So let's say that we are interested in a question like this. What is the probability that vortioxetine ranks first, bupropion second, and escitalopram third, which in fact is the ranking of these three treatments according to the odds ratios versus the reference treatment versus any reference treatment. Or another question of interest could be, what is the probability that vortioxetine, bupropion, and escitalopram are the best three treatments? So this is similar to the first question, but it is more broad. So it would allow vortioxetine, bupropion, and escitalopram to have any of the first, second, and third ranks. Another question would be, what is the probability that vortioxetine has better outcome value than that of bupropion, and bupropion has better outcome value than that of escitalopram? Or what is the probability that these three treatments have an odds ratio of 1.25 or higher against fluoxetine? Or what is the probability that they have an odds ratio of 1 or higher against fluoxetine, or in other words, that they are better in the conventional way that we define better between two treatments. So to answer such questions, we developed an approach which is described in this paper in BMC Medical Research Methodology. And the first step to answer such a question is obviously to perform a network meta-analysis, then to set a number of criteria like those that I showed before, then find the hierarchies that satisfy these constraints, and finally derive the estimated probability for each of those hierarchies. So for the third step in the approach, what we would do in order to find all possible treatment hierarchies and compute their probability of occurring is to sample from the distribution of the network meta-analysis relative treatment effect and calculate all the hierarchies that arise. So this is done exactly as it's done for probabilities of being at each rank by going one step back and getting all the hierarchies that arise. Note that computing all T factorial hierarchies would be very computationally intensive, but this in practice is not needed, because if a hierarchy is so rare that would not occur, then the estimated probability of occurring is 0. And what we would do would be to increase the number of simulations and see if it would appear, if we would get more simulations. So using one of the examples I showed before to show the approach, let's say that our question is, what is the probability that vortioxetine ranks first, bupropion second, and escitalopram third? Then, as said, we would derive all possible hierarchies in the network meta-analysis, and then filter those that satisfy this desired condition. And at the end, we would get those hierarchies that satisfy the desired condition and add the frequencies to a sum probability of the criterion to hold. So we have implemented this approach together with Gitos Varcher and Theodoros Papakonstantinou in an R package, which is in CRAN and is called animeRank. And I will now show how this package works. So the main functions are two, is the animeRank and the condition function, where the condition function is used as an argument in animeRank, which I will explain now. So the first question is animeRank, which specifies the frequencies of hierarchies along with their estimated probabilities and the probability that a specified criterion holds. And the arguments are t.nma, which can be either an object of class netmeta or a matrix with network effects which have been calculated elsewhere. Then we have condition, which I will show how to define it later. Then the variance-covariance matrix for the network estimates. Then a character called pooled, indicating whether the hierarchy is calculated for fixed effects or random effects model. The number of simulations, and small values, which is a character specifying whether small treatment effects indicate a good or bad effect. And then the output will be a list of the most frequent hierarchies along with their estimated probability of occurrence and the probability of selection, which is the combined probability of all hierarchies that satisfy the defined condition. And then the condition gets as input a character specifying the type of condition, and according to this type of condition we have some additional function arguments, and the output is not relevant, is the same defined condition and its arguments, and the reason that we want this condition is to insert it in animeRank. So we have programmed some types of conditions, but these can be also enriched with other types of functions. So here we have the same hierarchy function, which is that checks whether a specific hierarchy occurs. And the additional argument that we would need for this is a vector of a permutation of all treatment names. We have the specific position, which checks whether a treatment ranks in a specific position, which would need the name of the treatment and a single numeric. Better or equal, which would check whether a treatment has a position better or equal to a specific rank. Retain order, which checks whether a specific order is retained anywhere in the hierarchy. Bigger CIV, which is to answer a question I showed before about, for example, being bigger than 1.25 versus fluoxetine. And then we have these AND, OR, and XOR and opposite functions, which can be used to make more complex decision trees with the previous functions. So here is how it would be used. At the first we will perform network meta-analysis, then set a number of criteria, and with the condition function, and then with the animeRank function, check which hierarchies satisfy these constraints, and we will get how certain we are about each one of these hierarchies. So, for example, going to the package, we here is the depression data set. We have one row for each treatment arm, and we have the drug names, the sample size, and the responders. Then we prepare the data for network meta-analysis using the pairwise function. We then conduct network meta-analysis using netmeta. And here I want also to draw the forest plot against fluoxetine for the network meta-analysis results, so that you can see on the side the results versus fluoxetine and together with the criteria. So here, this row here sets the specific position function that for tioxetine is first. This one here specifies that bupropion is second and escitalopram is third. So the first criterion that we set here is that vortioxetine ranks first, bupropion second, and escitalopram third. So our first criterion is this and the second and the third. And then we run animeRank, we call it ranks A, and we have number of simulations 10,000. We specify that small values are bad. We have put the net meta object here as input, and the condition is criterion A. And then we print the ranks A probability of selection output that it is 0.09. So 10% that this criterion actually holds in our example. Then the second question that I pose is, what is the probability that vortioxetine, bupropion, and escitalopram are the best three treatments, which, as I said, is a different question. And in order to answer this, we would use the better equal function, so that vortioxetine is better or equal than third, so it's either first, second, or third. Same for bupropion and same for escitalopram. And then by using the end functions, we get this combined criterion B. And then we run again animeRank with condition being criterion B. By doing this, so here you see vortioxetine, bupropion, and escitalopram rank at the first three ranks according to their odds ratio. And then we have the ranks B object of animeRank with a probability of selection of 19%. So then the next question is, what's the probability that vortioxetine is better than bupropion and bupropion than escitalopram? So this, in other words, means that the order vortioxetine, bupropion, and escitalopram is retained. So we are using the retain order function. And then we again run animeRank with the condition being the criterion C. And we get the results to be 32.54%. And then our next question is about CIV, that vortioxetine, bupropion, and escitalopram are better than fluoxetine by an odds ratio of 1.25. Here we give it on a log scale, as it is required by the function bigger CIV. Same for bupropion and same for escitalopram. And again, we get the combined criterion for these three by using 10,000 simulations and criterion D as the condition. And the result is 44%. Whereas if we want to run the last question, which is that vortioxetine, bupropion, and escitalopram are better than fluoxetine in the conventional way, then we could either use this bigger CIV function by putting here 0, or we can use the retain order function, saying that vortioxetine is better than fluoxetine, and the same for the other two treatments, and get a 92% probability that this holds. So you see that this is much more probable than this criterion that uses a CIV, because it is this is a more strict criterion. And we have also Theodoros Papakostadinu has also programmed this non-R-Sine to facilitate the application. And here I can briefly show how this works using another example. So here is an example of 4 treatments for chronic obstructive pulmonary disease, where the primary outcome is mortality, and the 4 treatments are fluticasone, SFC, salmeterol, and placebo. Here is the forest plot against placebo. And let's say that we are interested in these 4 questions, whether the hierarchy is exactly SFC, salmeterol, placebo, fluticasone, which we would answer like this. So here you can download this example. This is what I have done, and you can upload the NMA effects and the variance-covariance matrix. So in the R package, you can either use a table for NMA effects and a variance-covariance matrix, or an object from NetMeta. Here, you cannot upload an object from NetMeta, so you have to upload the NMA effects and the variance-covariance matrix. And then at main, you can specify the number of simulations, whether small values are bad or good. So here, small values are good because the outcome is mortality. And then you can choose which functions you want to use. And here you can also put opposite, and then input the extra argument that is needed according to the function that you specified. So here we have this SFC, Salmeter, or placebo, fluticasone, and then you check choices, you see what you have chosen, and then calculate the probability, which here is 0.097. And you also get the probabilities of all hierarchies in the network. So here, because you have fewer treatments and more precise results, the probability of the first hierarchy is 28%, the second 21%, and so on. And all hierarchies that can appear in the network. So for let's say the second question, whether the order SFC, fluticasone, placebo is retained anywhere in the hierarchy, you can use the retain order, and then SFC, fluticasone, placebo, check choices and calculate, which is 0.63. And the third example is that salmeterol is second, so this would be specific position, and salmeterol is second. You can check the choices and then calculate that this is 41% probable of happening. And you can also combine by, for example, and say that you want also that fluticasone is among the best two options, so better equal fluticasone first or second, and then check your choices and calculate that this is not very probable to happen. So what we have in principle done is to provide a more generalized framework for asking ranking questions, but this framework does not translate to a new ranking metric that is attached to its treatment, but is a more general way to see how probable it is that some criteria that can be defined hold or not. And when I talked before about the criticisms, I did not mention another criticism that for ranking metrics, that is that they are not accompanied by a measure of uncertainty. And something that I want to note is that when we talk about uncertainty in ranking, we mean two things. The one is the uncertainty within each ranking metric, and the other thing is uncertainty of the entire treatment hierarchy. So regarding the uncertainty with each ranking metric, for example, this paper deals with this issue, where they have attached confidence intervals at SUCRAs and judge whether the ranking metrics are uncertain or not. But this has also a large discussion around this issue regarding whether we are allowed to attach confidence intervals and ranking metrics, which has to do with the appropriateness of the way that confidence intervals are calculated and of whether ranking metrics are population parameters or not. But I will not go through, will not go into this discussion. And then there is the uncertainty of the entire treatment hierarchy, which was firstly introduced, as far as I know, in this paper. And what they had suggested in this paper is to look at the shape of rankograms in order to see whether the entire hierarchy is precise or not. So, for example, in these two hypothetical network meta-analysis, which now they are indeed two hypothetical network meta-analysis, we have, for example, that here treatment A is clearly fourth, treatment B is clearly first, treatment C is clearly second, and treatment D is clearly third. Whereas in this network, we have the same sequence, but it is less probable because the rankograms are more flat. So one idea with the approach that I described would be to formalize this using our approach and see whether the magnitude, let's say, of the most frequent hierarchy is big or not. Here it would be very big, and here it would be less big, to see whether the entire treatment hierarchy is precise or not. Or one could think of other ways, like, for example, summarize the hierarchy matrix, which would be like this matrix here, by either taking the variance or another metric, or take the ratio of the most frequent hierarchy, this one, versus the second, versus the third, and so on, as a measure of precision of the entire hierarchy. But a drawback of all these approaches would be that they all depend on the number of treatments. And by taking ranking more near to a decision question, this would also mean an alternative way of judging precision. So instead of looking at specific metrics, it would be an alternative way to look at the certainty of the specified criteria that we set. So one could think of a scenario that examples with that it could be a network meta-analysis with imprecise results in general, but for the specific criteria that we have set, these are associated with certainty. And this could be relevant for decision making. And this is actually the scenario in the antidepressants network that I showed, where each individual hierarchy had a very low probability of occurring, but the criteria, some of the criteria that we set were quite certain. And a last criticism that ranking metrics are associated is that they do not account for multiple outcomes, which I would say it's not a very relevant criticism, because also multivariate network meta-analysis is not very common. But one way to deal with this would be to extend the approach that I described for multiple outcomes, either by doing it separately for different outcomes. For example, seeing that the hierarchy BCDA has a 28% probability of occurring for outcome A, then 10% for outcome 2, and 35% for outcome 3. Or sample separately or simultaneously from 2 or more outcomes and measure the frequency for each one of the possible hierarchies for all outcomes. But in order to do this, we have to have exactly the same treatments for both outcomes, which is rare in practice. And then another future direction would be to incorporate benefit-harm considerations in the approach. And something that we also would like to do is to apply it to a clinical example. So here are some other papers that have used approaches based on clinically important values, benefit-harm considerations, and multiple outcomes that have also set the ground and have, in a sense, influenced also the approach that we took and I presented here. Thank you very much for your attention.